All right, everybody, welcome to officially lesson number 2, but really the third video in this quadratic series for 20-2. We're going to talk this time about factoring, and it's one of the more involved algebraic processes that comes out of Math 10, and there's a big reason for that because a lot of the things that we can do in the 20-level math courses and the 30-level math courses, well, they really depend on factoring. It's one of the important skills that comes out of that Math 10 course, because we know that it's in everything after that, right? It's all over Math 20, it's all over Math 30, and this is where it really starts to have some application. So before we started to do like the factoring piece, well, we kind of need to remember how to multiply some polynomial expressions together, especially if I've got some binomials being multiplied together. And again, I know these are two binomials in these set of brackets because there's two terms, right? Again, bi is the prefix meaning two, and you can think about nomial as really being your terms, right? It's not a great definition, but it is the one that we can use to really talk about this. So one binomial is x plus 3, the other one's x plus 2. And if you remember the distributive property, we can multiply this out by taking everything in one set of brackets and multiplying it with everything in the other set of brackets. But remembering that it's really those plus signs that separate the terms. Multiplication does denote something as being a term. So just be careful when doing this if it's something like 2x on the inside of the brackets. The whole term would get distributed. So let's multiply this out, and I'll keep it color-coded so that we end up taking the blue arrows, multiplying them to get x squared plus 2x, and the green ones multiply together to get you plus 3x and plus 6. Now I can collect some like terms in the middle, so if you follow the same pattern I did, you're still going to have two terms, usually two terms that you can collect together. So I've got x squared, because that's the only term that has an x squared. The 2x and the 3x can go together. You have 5x's total plus 6. So there is my polynomial expanded now. It has the form of that quadratic equation which we saw in the last couple lessons, right? Something being squared, there's an x term in the middle, constant on the end. So I know right now that the y-intercept of this is actually 6. I know it opens upwards because x squared is a positive 1. What I don't know, however, from this are the x-intercepts. And this is where factoring becomes super powerful. Now, I could take a polynomial, a quadratic, right, a trinomial, and, I could represent it in factored form. And there's a few ways to do that. So this is just a lot of information. It's very word heavy. So I won't spend too much time on this because we'll do a few examples here together. But, when it's possible, see if there's what we call a greatest common factor first, right? If there's some factor that you can take out of all three, well, it tends to make the numbers a little bit smaller and easier to think about. So a greatest common factor here could be 3, and you're going to be left inside the brackets, your resulting trinomial, as x squared minus 9x. I believe that works out to be 18. So let me check. 54 divided by 3 is 18. Okay, so essentially what happens when you take a greatest common factor, everything's really just getting divided by 3, and that 3 needs to stay on the outside as a resulting, coefficient, or else I change the value of things. So that helps make that polynomial a little simpler. But then there's a method we could use to factor it called the sum and product method. And what it asked us to do is find two numbers that multiply to the constant, but those same two numbers have to add up to the coefficient of my x term. And there's a couple examples that are worked out for you here, but we'll do some together so we can really see this in action. So I've got a polynomial here, x squared minus 10x plus 16. Now if we're going to go factor this, we need some numbers to satisfy some conditions for us. And I always like to start with this with a little bit of a picture, because it tends to help people visualize what it is we're actually doing. So it's kind of set up like an algebra tiles grid. I won't draw the tiles in, but the way that they worked is that you had x squared as one of your terms, and it was always in the top left corner of this grid. The constants were always in the bottom, and it was our job to take our x's and arrange them into the two remaining spots, right? Those two blanks there. Now I don't really know what the split is. I don't know if it's supposed to be, 1 and 9 because I have 10 negatives. I don't know if it's 5 and 2. I don't know if it's, 5 and 2, 5 and 5, or 8 and 2. I really have no idea, but it's this constant number that's going to tell me, because however I arrange them in here, those two numbers have to multiply to give me my constant. Because if you remember, the way that this works is essentially a grid that gets us multiplication. So if I think about splitting up those 10x's, well, I can split them into a group of -8 and a group of -2. So in total, in green, I have negative 10x's. But when I multiply 8 times 2, I'm going to get my 16. Okay, so it is a pair of numbers that may work. And again, what we would do from here is take each row of them and look for the things that they have in common. So in that red box, those two terms of x squared and -8x have one thing in common. It's an x. I could do the same thing for the row underneath, recognizing that, hey, those two numbers, 2 and 16, have something in common, and it's a 2. And I could try the same thing for the columns as well. Okay, so the purple column, the first one, in common they have an x. And the last column, in orange, they have in common an 8. Now I can go around and check if this actually works out. If I take my pink 2 and my orange 8 and multiply them, I get my blue 16. But the problem is the x in purple across the top, the pink 2 on the left side, well, they don't multiply to give me negative 2x, they give me positive. So my pink 2 actually has to be a negative 2, and by the same logic, the 8 has to be a negative as well in order to make the negative signs work out. The numbers don't change, but now everything multiplies out to what it's supposed to. So the way that factoring works as like a visual, the two factors are written across the top of this rectangle. So let me move this picture down. Okay, so this is one factor, so factor number 1. And the one down the other side is factor number 2. And what they actually do is they multiply together to give us our original polynomial in the middle. Essentially, this is the area of a rectangle. So if I take the length and the width of it, multiply them, I get this polynomial expression. By taking that area apart, well, now I know that x minus let's do x minus 2 first, doesn't matter. X minus 2 multiplies with x minus 8 to give me x squared minus 10x plus 16. Okay, so we factored this, but sometimes that can be tedious to draw out and figure out what goes where. So there's the sum and product method, which we talked about previously. So if I think about doing that for b, and I'll show you both methods here, well, think about two numbers that are going to multiply to give you negative 21, but the same two numbers are going to add up to the number in the middle. So they're going to add up to a positive 4. And you can think about all the combinations that multiply to 21 first, right? You could do 21 and 1, you could do 3 and 7, and I think that's pretty much it. 7 and 3 is a good pair of numbers that will do this, because they are 4 apart from each other as well. I just have to make sure the signs work out. So if we use a positive 7 and a minus 3, right, those two numbers will multiply to negative 21. They'll also add together to positive 4. So I know I found the numbers that'll do this. And once I find them, as long as my x squared coefficient is 1, right, I can jump straight to these two factors. And essentially, if I know the two numbers, I know the factors. One of them is going to be x plus 7. The other is x minus 3. The variable goes in first. The numbers you found along with their signs, so those integers, go in second. It's completely factored. You could do it using the picture as well, and what you'll notice is you're going to have an arrangement of x's where you're going to have 7 x's in one, negative 3 x's in the other, and everything is still true with regards to that picture. So it really doesn't matter which way you do it. Many people are going to have one preference over the other. Now, we'll do all of them here so you can see them. I think C is actually an exact repeat of B, so we won't do that one. A little bit of a typo in there. But we can definitely do the bottom three, because now the numbers have changed. Right? Think about that coefficient of x squared now. Well, now it's not a 1 anymore. We can try to make it into 1 if all of those terms are even. Well, let's factor out a 2 first. So divide every term by 2. It remains in the brackets. And again, all of the same things are true. Think about what multiplies to negative 35, but adds to negative 2. 7 and 5 seem like good options. And I need to make sure the signs work out also. I want to add to a negative, so make your larger one of the two the negative number. Add them up for negative 2, multiply for minus 35. All looks good. So our 2 is going to stay there because it was a greatest common factor between them, so I have to keep it in order to make sure things are equivalent. But inside the set of brackets now is where our 2 factors are going to go. And again, remember that factors are just things you multiply together to get something else. So the 2 things we multiply, we want to be able to get our original polynomial. So the variable goes in first. It was x that we used. Those integers go in second. Now it really doesn't matter which one goes first because multiplication can happen in any order. So I could also write it as 2x plus 5, multiply that by x minus 7. Right? It really doesn't matter which way you write it. They're the same thing. You can try this for e as well. But notice now this is an x cubed, so really this isn't a quadratic equation anymore. Right? Because quadratic equations have something with a degree of 2. This has a degree of 3. So let's see if we can take out something that they have in common. Now all 3 terms have multiples of 3, so 3, 9, 12. They all have x's as well. So if that's my greatest common factor, if I divide those 2 terms, the 3x cubed by 3x, well, what I'm really left with is x squared. 9 divided by my greatest common factor of 3 leaves me with 3. X squared divided by x leaves me with x. And then I've got a minus 4 left over by the same process. And again, you're going to try to find 2 numbers that multiply to negative 4, but add to 3. And really the only combination that works is some version of 4 and 1, where this time the 1 is going to be your negative, because 4 plus a negative 1 will get you 3. Multiply those integers for minus 4. So really this is the same. Leave your common factor alone. Your polynomial gets split into 2 factors, where the letter goes first and the integers go in second. So there you go. This time it has 3 factors. So here's factor number 1. This one is factor 2. And the last one, x minus 1, is factor number 3. So this one would be very difficult to do with that grid picture that I drew before. Well, because if there's 3 factors, this would essentially be something that's 3-dimensional. Not necessarily a rectangle, but it could be a rectangular prism instead. There's 3 different dimensions here, length times width times height. The application is a bit different. The process is the same, so you can try it here as well. Again, each multiple is of 3, so you get x squared minus 7x plus 10. The process is no different. Find out what multiplies to positive 10, but adds to minus 7. It looks like a combination of 5 and 2, where both of them this time are negative. Right, adding them up gets me minus 7. Multiplying them, the negatives will simplify, and they'll be opposite pairs, right? So a negative and a negative make a positive is what they simplify to. And then I can write my factored format as x minus 5 multiplied with x minus 2. So really no different. As long as I get my squared terms coefficient to 1, I can do it like this every single time. Sometimes you can't get it to 1. There's a bit of a longer process we have to go through. But we can work with that a little bit later on. Okay, once I have it in that factored form though, I can draw it pretty easily. Now, to sketch the graph of this, we need to factor it to determine the x-intercepts. if I have it in a factored format, I could find the x-intercepts pretty quickly. Now, another word which you'll see thrown around quite a bit are zeros. So the x-intercepts are also sometimes called zeros because they are the places on the graph where the y value of those points is 0. Right? They're right on the axis line. So if you have it in factored form, you can essentially take each of your factors and make them equal to 0. And the logic behind this is, the logic is pretty good. If you think about having an expression that says 2a is equal to 0, well, the only real possibility for a here is that a has to be 0 for this equation to be true. But what happens if you have two separate variables? Right? What happens if it's a multiplied with b equals to 0? Well, on one hand, a must be 0. Right? A must be 0. B doesn't have to be. It could be, but it doesn't need to be. Right? If a is already 0 and b is something like 5, well, 0 multiplies with 5 to get 0 anyways. So b doesn't have to be 0, but if b is not 0, then a has to be 0. The other case is also true where a is non-zero. That means b must be 0. So what you can really conclude here in this case is that at least one must be 0. Right? In order for this equation to be true, either a or b have to be 0. If both of them are, it's still true, but at least one of them has to be in order for that to be true. So the logic here is that if I have something, and I'll give you an example here, if I've got a function, right, y is equal to, and I'll write it in factored form, I'll pick one of the examples we had before, maybe it's something like x minus 5 multiplied with x minus 2, something that we factored. Well, if I want to find the x-intercepts to this, what I'm really going to do is let y be equal to 0, which I can rewrite this equation then as 0 equals x minus 5 multiplied with x minus 2. Now think about this as being the same format of a times b. And I wrote a again. a times b. Again, one of them has to be 0. Both could be, but at least one of them should be. And what you can do in a situation like this is take each of those factors, one of them's x minus 5, make it equal to 0, or x minus 2 has to be 0. Again, we said at least one of them has to be. So if you solve these little tiny equations that come from your factors, you'll know that, hey, if x is 5, that'll be the value of x that makes everything 0 here, because if I put it back into the original equation, one of my sets of brackets will say 5 minus 5, they'll simplify to 0. Which means 0 multiplied by the other set of brackets, no matter what it is, will be 0 anyways. So there's one of my x-intercepts. The other one, by the exact same logic, is 2. And if I even graph this, and I'll even put it in, in the factored form at the brackets, so x minus 5 and x minus 2, what you'll see is, I gotta zoom out here. Oops. Go back to normal. What you'll see is this graph has one of the x-intercepts on 2, just like we said it would, and the other one's on 5, right? 1, 2, 3, 4, 5, just like we said it would be here as well. So if you can factor it, you can find the x-intercepts pretty easily. Okay, so let's do a full example where we draw the whole thing, find all the things we talked about previously. Really, we're going to put it all together. So sketch the graph of this function, y equals x squared plus 2x minus 8. And step 1 is to factor it to find your x-intercepts. Okay, so we'll factor this first. So find two numbers again that do those conditions, multiply to minus 8, add to 2. 4 and 2 seem like a good combination, and we're going to use a negative 2 here to make this work. So I know that if I jump to my factored format, it's going to be x plus 4 and x minus 2. Right? Those are my two factors. And if I'm going to find the zeros, I'm going to let the value of y be 0. Right? Let y equal to 0. So my equation then will say 0 equals x plus 4 multiplied by x minus 2. And again, you're going to take each of those, I'll move it up here, and make them equal to 0 to find the specific x values that make it possible. And there's going to be two of them, because I have two factors, I'm going to have two intercepts. One of them is going to be x is equal to negative 4 if you take a 4 and subtract it on both sides. I'll do that in red. Right, minus 4 simplifies on the left and moves over to the right side of that equal sign. The same logic is true with the other one, except I'm going to add a 2 to both sides for them to simplify. Right, it creates a 0 pair, and then I'm left with x is equal to 2. So there's my two intercepts. Now if I know my intercepts, I can also determine my axis of symmetry. It's the line that's halfway in between those points, and what we said we could do, so here's our axis of symmetry. What we said we could do before is take those x-intercepts, add them together, and divide it by 2. So negative 4 plus 2 is negative 2. Divide that by 2 for negative 1. So therefore I know that x equals negative 1 is the axis of symmetry. Well, if I know what the axis of symmetry is, and I know the line that makes my vertex, I know the line that goes through my vertex, well, I can actually find the vertex out because I know the x value of it. So we'll take that x value, we'll put it into our original equation, right? So y equals x squared plus 2x minus 8. So we're going to let x be equal to negative 1. Because I know that'll be the x coordinate of my vertex, so plugging it in will get me the y coordinate of the same vertex. Right? So y is going to equal negative 1 squared plus 2 multiplied with negative 1 minus 8. So we can put all that into the calculator at the same time, as long as you use brackets on the square, because it won't square the negative sign if you don't, and that's a problem. And then subtract 8, so we're going to end up with minus 9. Okay, so now I know, therefore my vertex, x coordinate is minus 1, y coordinate is minus 9. Super helpful. Y-intercept is an easy one, because if I can look at the original equation, that's just going to be my constant. I really don't have any work to do, so I know that that y-intercept is going to be when x is 0, y is minus 8, right? Straight from the constant in that equation. All I'm asked to do now is graph it. So we'll put all that information on there, we'll graph it, and then we'll look at our calculator to see if we did it correctly. So let me zoom out enough here. All right, so we'll put the zeros on there first. One of them's at 2, the other's at minus 4. Our symmetry line should be right along x is equal to negative 1. Okay, so 1, 2, 3 away, 1, 2, 3 away. So I know that's our symmetry line on x is equal to minus 1. Our vertex, we know it as well, is negative 1, negative 9. That was in black. So right on our symmetry line, way down at negative 9, is the vertex. The y-intercept we said was at negative 8. So I've got my 4 critical points again, my 2 intercepts, my vertex, and the y-intercept. Sketch it as best you can. Again, doesn't need to be perfect, but there's the general shape of this. And if I graph it to check, where was it? Okay, so x squared plus 2x minus 8 graph. Something like, looks nothing like the one I drew because my graph is terrible, but all the same information is there, right? X-intercepts are in the same spot, vertex in the same place as a minimum, and there's your y-intercept, so it all fits. The only thing we didn't do is domain and range. So for x, again, it could be any value. For y, it has to do with the vertex, and again, we drew our vertex way down here with a y value of minus 9. So everything else about this graph is bigger than -9. And really, to be technically fully correct, I should also say that y is any other real number. But it has to be bigger than or equal to my minimum, right, to -9. Okay, so same as before, can determine all of those same things, which we have done before. The only part that was new was finding the x-intercepts by hand. Right, I wasn't given that information, just the equation. Other than that, nothing was really different. Okay, we can sketch this one out as well. And we can sketch out 3 also. So I can, as long as I know my equation, I can draw it. So we got to go find out all that information. So there's 4 points that we really need to find. Right, we really need the vertex, we really need a y-intercept, and we really need zeros. Really, there's 4 things we have to find. So let's find the easiest one first, the y-intercept. Okay, the y-intercept is your constant. So therefore, if x is 0, the y-intercept is 15. Pretty easy to find. I know it's a constant because it's 15 right on the end. So I'll graph that one right now. If x is 0, y is 15. Next easiest one to find, I guess would be, yeah, I need the x-intercepts here. So I need to factor this. Okay, so we'll factor this first. So our function of x is equal to x squared minus 8x plus 15. So finding the 2 numbers that multiply to 15 and also add to -8 are going to be some version of 5 and 3 where they are both negative for this to happen. So I know that my function has a factored form of x minus 5 multiplied with x minus 3. And again, to determine those x-intercepts, your function should have a value of 0. Nothing else really changes. But now I can say that x minus 5 should equal 0, or 0 should equal x minus 3. There's 2 possibilities here. So one of them, 5, is actually the value for x, and the other one, 3, is the value for x. So I know my 2 intercepts are x equals 5 and x equals 3. So there's one at 3. There's the other at 5. In order to determine your axis of symmetry, it's the halfway line between those 2. So you could do it by hand. You could look at the graph and realize that there's only one number in between there. So it really should be right along x is equal to 4. Right, there's my symmetry line that will cut it in half. The only thing I have left to find is my vertex. So x equals 4 is your line of symmetry. So in order to find your vertex, we're going to let x, we'll let x be equal to 4, and we're going to put that into our function. So let me zoom in a little bit. So the function will have a value when the input's 4 of 4 squared minus 8 multiplied with 4, by 4, and then we'll add 15 to the bottom. So 16 minus 32 plus 15. So 16 subtract 32 is negative 16. Add 15 to that for minus 1. Okay, so now I know what my vertex is. When x happens to be 4, that y value that goes with it is minus 1. So there's my vertex at 4, negative 1. So I've got my 4 important points. The 2 intercepts in purple, my y-intercept in blue, the vertex in green. I've got enough to draw the graph. And again, it's just a sketch to see the shape of it, so it does not need to be perfect at all. Okay, it'll look something like this. And maybe I'll extend the other side here. Okay, something like that. Okay, and you can graph it as well. Let's change this up to minus 8 x plus 15 graph. Okay, so there you go. Now my window's obviously changed a little bit, so this one only goes from -3 to down to -2 as a y, but basically the same shape. Part B says determine the domain and the range. So domain, again, always the same thing. No restrictions on it. But for y, remember that it always comes from the vertex, right? The y value of your vertex is -1. This is a minimum, so everything should be bigger than it. Y is greater than or equal to -1. Y is any other real number outside of that. Okay. So very, very similar for the one we'll do underneath as well. So if you want to try any of them, really just pause the video and try it out and then, hit play. But we'll do this the same way. Easiest thing again to find first is the y-intercept. Right, in this format, that the constant number will tell me what the y-intercept is. Now there's no number here that doesn't have a variable, so I know that my constant is 0. So therefore my y-intercept should be right on the origin. Right, really, it's like saying there's a +0 attached to this. So I know my y-intercept already is right on 0, 0. That was good. X-intercepts come next, I suppose. And then we can go find the vertex. So x-intercepts mean that we're going to let y equal 0. Actually, let's factor this first. So y equals -3x squared plus 6x. Look at what they have in common, and you can take a -3x as a common factor, so that you're left with x minus 2 on the inside of your set of brackets. And you can always double check by distributive property if you've done this correctly. So -3x and x make -3x squared, so that's good. 3 and 2 make 6. Negative and negative simplify to a positive, and my x is there where it's supposed to be. So I know this is good. And again, you can make y 0, and you can use each of your factors to solve for your x-intercept. So for one of them, -3x should be equal to 0, or the other option, x minus 2 should be 0. And if you solve each of these in their own respective way, well, I'll divide the first one. Both sides get divided by -3. So one of my zeros, or x-intercepts, is, well, 0. The other one, add a 2 to both sides to simplify, and x is equal to 2. So if you throw those on your grid, well, I already had one of them, right? My y-intercept and x-intercept overlap here, which is fine. We've seen that before. The other one's at 2, which makes my line of symmetry right down the center when x is equal to 1. So no calculation needed for that one. I could tell pretty quickly. So in order to find my vertex, we're going to let x be equal to 1. That's what's going to go into our original equation. So y is going to equal -3 multiplied by 1 squared plus 6 multiplied with 1. So that works out to be -3 plus 6, y value of +3. Okay, so look where your vertex is this time. It's up on the top, so I know that this is going to be opening downwards. It'll have that sad face kind of look, and I know that because my original equation also had a negative. So super helpful. Again, I've got all my 4 critical points on there. The 2 intercepts in red, my y-intercept in purple, and they matched one of my x-intercepts, my vertex in green, so I've got enough for my shape of this. And again, not perfect, but just need to see what it looks like. And again, domain and range are the same. X is any real number, y comes from the vertex. Since this is a maximum, y has to be less than or equal to that y value of 3. Right? That's the y value of my vertex. So everything kind of fits exactly the same way as we saw before. So if I'm given the equation, I can make the graph pretty easily. But what happens if you're just given the graph and we have to go backwards to figure out what our equation is supposed to be? Because now I'm really not told a whole lot of things here. And, by looking at the graph, it's not as easy to figure out what that value of a is supposed to be, really, if there's a common factor or not, or what my coefficient of that squared term is supposed to be. Really, that's what we're looking for. So there's some instructions up on the top that will help, and it says when determining the equation, start by using the form that looks like this, the factored form of it, where we're going to assume that we have something on the outside, that a is a common factor. Sometimes it's 1, sometimes it's not. So let's assume that it's not until we can find out what it is. Right? Assume that it isn't, and assume you have something other than 1. And in order to do this, we need some points. Right? The two that we need are the x-intercepts for sure, and then we just need some other point on the graph. Some other point. It doesn't matter what it is, but just some other coordinate pair. Okay, so using the graphs, determine the function in factored form that defines the parabola. So again, we could start by assuming that this is what our formula is going to look like. Now, I've written in two variables here, r and s, and what they are, really they're just x-intercepts, right? They're just the variables that represent what's going to go there. So as long as I know what the x-intercepts happen to be, we'll just find some other known coordinate to figure out the only remaining variable. So on this graph, I know what my two intercepts happen to be already. One of them is where x is equal to -3, which let's call that r for one of the intercepts. And for the other one, well, we'll use the other x-intercept where it's equal to 1. Let's call that one s. And it really doesn't matter which one we call which. It's not a left side, right side thing. That's completely arbitrary as to which one it is. Okay, so let's just put those in right now to see what this looks like. So y equals to a, x minus. Now the negative sign is built into this. If r happens to be negative, which for one of our cases it is, I have to insert that negative sign as well. And on the other one, this is just x minus 1 because it was a positive. If you simplify this slightly, you get x plus 3 and x minus 1. So you can see that the signs are a little backwards. Right? My intercept for one of them was a -3, but in that equation it looks like a plus sign. The same thing is true for the other one, but it looks like a minus. Okay? So I'm not totally done yet, just because I need to know what that value of a is. Right? It could be 1, it could be literally some other number. But in order to figure it out, just pick literally any coordinate that you can tell from the graph. Could be a y-intercept, could be the vertex. It doesn't matter as long as you know the coordinates perfectly. So I'm going to pick the y-intercept to do this, and the only reason I'm choosing it is because it has an x coordinate of 0, and zeros tend to make things a little easier to deal with. And if it's just some point, well, it's an x and a y, right? So now I know the other two variables, x and y. So put them into your equation. And what you're going to see is you'll get 6 is equal to a, 0 plus 3 multiplies with 0 minus 1. So the only variable you have here is a, which means now you can solve for it. So 6 is equal to a, 0 plus 3 is 3, 0 minus 1 is -1. So if you simplify the right side of your equal sign here, you're going to find that -3 multiplied by a is equal to 6. Divide both sides by a -3 to simplify, and you'll see that -2 is now my value of a. And if you used a different point, you'd see the same thing. So now I know what my equation is going to look like. So therefore, y is actually equal to -2 x plus 3 multiplied by x minus 1. That is the equation that will do this. And if you want to double check you're right, graph it. Right, -2. Put in the brackets even. You don't even have to multiply it out. Your calculator will do the work for you. And you'll see the same thing. Right? Let's just go calculate the vertex. It should be at -1, +8. So second trace, option 4 is maximum. Go left side, then right side. Enter, enter. -1 and 8. Exact same vertex as this picture, so I know I've done this correctly. Right? You can find the y-intercept as well. Second trace, option 1 is value. Put in 0, There it is at 6. So you know the equation's the same when you see those 2 points on there. Okay, so really only one thing to find. We're just going backwards a little bit with all the things we know. Now when there's only one x-intercept, really it's the same thing, except you just have the same factor twice. So I know it says here that it's really y equals that a number, that common factor, x minus an intercept squared, but that's really the same thing as saying y equals a x minus r multiplied with x minus r. So it's the same intercept, it just occurs twice, which isn't to say there's one. It's a concept that comes up in Math 30 where it has a multiplicity. Essentially it's just duplicated. The same point happens 2 times. So if I know what that intercept is, just like before, well, my intercept here is x equals -2, so I can make it say r is equal to -2. So if I put that into substitute to simplify, well, I'm going to have x minus -2, and then the other factor is honestly the exact same. So when I simplify this, it's just a x plus 2 squared. Right? The fact that I take something and multiply by itself is why it's squared. And again, I just need some other coordinates to plug into this. Could be a y-intercept. It can't be the vertex this time, because that was also my x-intercept, and it's just going to make everything zero out and simplify to nothing. So pick a different point, and I'm going to pick the y-intercept one more time here. So it's just another point I can see clearly that lines up perfectly. You could pick -4 and 6 as well. That should work. But 0, 6 will also work. So make y 6, a is unknown, x is 0, plus 2 squared. So you can solve for a now, because 6 is going to equal to 4a. Divide both sides by 4 to simplify, and you'll find out that 3/2 is actually your a value here. So it's a little bit of there is a fraction involved, which is totally possible. So here my equation in that format, y equals 3/2 x plus 2 squared. And again, we could graph this to double check, so let's do that before we wrap up. So 3/2 x plus 2 squared, graph. Okay, there's basically the same picture. Let's find our y-intercept when x is 0, y is 6, so that looks good. Find your vertex, which is a minimum, so option 3. We'll go left side of it, then right side of it. Enter, enter. There's your vertex at -2 and, well, basically 0. It's just that it's written in scientific notation with a number that's so small, so even if I did it again and found that minimum, my calculator will probably tell me, like, you know, the couple decimals are off, but it might even just say 0 this time. So there you go. It gets like approximately exactly, which is why we can round it. So -2, 0. So exact same function given to us, and you know, I could put in a value of -4 as well just to check. And it should tell me it's 6, which is this other coordinate point on the left side. So I could have used that point to do this as well, and it would have worked the same way. So a lot of things I can do with just a graph. We can figure out all of this stuff, which is basically exactly how we started to learn about all of these quadratic equations. And again, you'll see your summary on the bottom. So this is a really, really good summary that puts together everything we talked about. So if you ever need to come back to it, you know, you're working on something and you need to remember all these things, this is a really good page on bottom of 15 there, or top of 15 I should say. But again, there are all of your practice ones underneath, just like before. So you'll find all the links up above. So we'll see you in the next one. Until then, take care.